Hi guys, welcome back to my channel. In this video, I'll be taking you through HopitalsRule 2. HopitalsRule helps us to solve indeterminate limit forms, indeterminate limit form, and is an application of differentiability. So, in HopitalsRule, we apply differentiation to solve indeterminate limit forms. How do we do that? So, under this, we have rule 2. So indeterminate forms, we have different forms, and root 2 is handling one type of form. So let's see. Root 2 deals with products. Example, if I give you 0 times positive infinity, what's the answer? Now, infinity is an assumed large number, so you cannot say that 0 times infinity will be 0 just like that. So we classify this as an indeterminate form. For that reason, L'Hopital's rule will handle functions that will give limit outputs at 0 and positive infinity. So what the rule is saying is that if you have two functions f of x and g of x, and I find the limit of f of x as x approaches a to be equal to 0, and I find the limit of g of x as x approaches a to be equal to plus or minus infinity, then the limit as f of x multiplying g of x as x approaches a will be equal to limits as x approaches a of f of x over 1 over g of x. In summary, this part is the condition. The condition is saying you should have two functions. So the function given should be decomposed into two separate functions, f of x, g of x. When you find a limit separately as x approaches the point where you are interested in, you should get 0 for one, you should get positive or negative infinity for the other. Once this is satisfied, you can go ahead to use the root 2. So in summary, you can have this as your root 2. It says that when the limit of the product of two functions f of x, g of x as x approaches a, where the f of x and g of x satisfy what is here, then the solution will be limit as x approaches a of f of x over 1 over g of x. So we simply express product to quotient. So root 2 is all about product to quotient. Remember that what you have done here, you have not done anything. If you have f of x, right, over 1 over g of x, this is the same as f of x. This division, right? So I'll multiply g of x over 1 because you reciprocate what you have here. And this will give you f of x multiplying g of x back again. So you realize that there is no effect. We are only trying to express it for easier simplification. Let's take this problem. Evaluate the natural log of x multiplying x limits as x approaches 0 of this function. So let me do it. So I have limit as x approaches 0 of x multiplying natural log of x. So how do we solve this problem? You realize that these are two separate types of function. X is a monomial, natural log of x is a logarithmic function. So I can easily break this into two separate functions, x and natural log of x. So I will just first do my preliminary test by finding the limits separately as x approaches 0. So limit as x approaches 0 of x, what is it? So limits as x approaches 0 of x. So this is simply equal to what? 0, right? So this is simply equal to 0. Then we look out for limits as x approaches 0 of the expression natural log of x. So what do you get for this? So we find limits of natural log of x as s approaches 0. So we realize that this will be giving us what? An infinity, right? Yeah, so we move straight to solving this using the root 2. So using the root 2, I said you are only going to express this as a quotient, okay? So you're going to have limits as x approaches 0 of, now expressing this as a quotient, you need to be very careful. You have to choose one which will give you a very easier simplification, which we call calculation efficiency, okay? Calculation efficiency or computation efficiency. So you need to take the one that will give you a high accuracy and also easier and less errors, okay? So realize that natural log of x can easily be differentiated when it is standing alone over, then I'll change the x to an inverse 1 over x. Yes. Once I get this, this looks like the rule 1. The next thing you are supposed to do is to differentiate this separately, differentiate this separately. Then after we apply our limit value, that's all. So doing the differentiation, I'll have limits as x approaches 0 of the expression. When you differentiate ln x, you're going to get 1 over x over, when I differentiate 1 over x, I'll simply have, this is the same as x to the power negative 1. So I'll multiply and I'll have negative x to the power negative 1 minus 1. This gives negative x minus 2, right? Also the same as negative 1 over x squared, right? So I'll simply carry my negative 1 over x squared. Further simplifying, I'll have limit as x approaches 0 of 1 over x times x squared over 1, where my negative is here. X goes into itself 1 and cancel here x. So this gives me limit as x approaches 0 of negative x. And obviously this gives me 0. And that is the end of this video. Thank you for being with me. See you in the next section where we'll be handling the 3.